Stochastic Gradient Descent. This tool provides visual insight into the stochastic gradient descent, or SGD, algorithm. To better understand the stochastic gradient descent, it is suggested that you learn the gradient descent first if you have not done it already. Please use the Site menu to visit the gradient descent section to learn about it. Let's quickly refresh the gradient descent algorithm. In gradient descent, we calculate the gradient or slope of the loss function by considering all the examples in the dataset. Then we update the model's parameters to move in the direction of the steepest descent of the loss function. This approach is great if the dataset is not very large. If the size of the dataset starts approaching thousands and millions of samples, the better option is to use the stochastic gradient descent algorithm. In this algorithm, instead of considering the entire dataset at once, we pick a small subset of examples from the dataset and calculate the gradient and other parameters, based on the subject of examples only. We repeat this process over the entire dataset. Typically, the subset examples are selected randomly. Due to this random dataset aspect of the algorithm, it is called stochastic, which means involving a random component. The subset of examples is called a batch. This tool will help you understand how the stochastic gradient descent algorithm works. Let's explore it. Here is the x, y data, the equation of the regression line representing the data, the initial values of model parameters a and b, and here is the learning rate alpha. As the stochastic gradient descent uses batch as the number of data samples used in each iteration, this is where you can select this batch size. Let's leave the default values for all these parameters. Here is another concept used in SGD, which is called momentum. We will explain this term later. For now, momentum is turned off. Let's initialize the algorithm or model by pressing the initialize button. The XY data is ported over to this table, and its scatter chart is displayed over here. Now let's run the first iteration by pressing the next button. This green highlighted area represents the calculation scope for model parameters, meaning only 2 data samples or data rows are being used in this calculation. For these 2 data samples, we calculate the predicted y value based on the last values of a and b, which is 1 and 1. The average delta between the predicted and actual y values, and the loss function based on this batch of data. We use this formula to calculate the loss function L. Next, we calculate the gradient of this loss function with respect to each model parameter a and b, as shown by partial L by partial a and partial L by partial b. Again, we calculate these values as an average gradient or slope for a 2-sample batch. Finally, we calculate the model parameters a and b. We calculate these gradients and the a and b values using the a and b of previous iteration, the learning rate alpha, and the new gradient or partial derivative values. Here, we can see the epoch number, batch number, the last loss, and the latest values of model parameters a and b. In this chart section, we have the XY plot showing the scatter plot of XY data and the regression line based on the recent calculated model parameters a and b. Let's perform another step of stochastic gradient descent by pressing the next button. Please note that a new batch of data is selected, as highlighted from this green section, and all the intermediate values and the model parameters are calculated and updated using the new batch of samples. The batch number is also updated accordingly. As we keep pressing the next button and we keep taking more steps through the algorithm, the model parameters and the regression line start converging to minimum loss function and closely fitting the data points. Finally, after a few more epochs, the loss becomes almost zero and the line fits the data perfectly. Using the chart dropdown, we can explore additional charts like loss, parameter A, and parameter B. Let's switch back to the XY plot. Now let's talk about the with momentum variation of this algorithm. In some situations, depending upon the initial values and the learning rate, the regular SGD algorithm does not produce the required results as the loss function starts diverging instead of converging or oscillating too much, or it can get caught in a local minima. To overcome these issues, a momentum factor is introduced which not only takes into consideration the latest gradient values, but also its history. Please read the documentation of this algorithm to get more insight into this algorithm along with the mathematical equations involved. For your reference, these are the equations used to calculate the parameters A and B using momentum. To demonstrate the aspect of the momentum where it helps overcome the loss function divergence, let's select A as 1, B as 2, and alpha as 1.0. We will leave the batch size as the default value of 2, and the momentum will remain unchecked. Let's initialize, and let's select the chart type as loss. Now let's run a few iterations, and you can notice how the loss function has started diverging and getting out of control. Obviously, this is an undesired solution. To fix this issue, now let's turn the momentum on by selecting the with momentum checkbox. We can initialize the algorithm again and run a few iterations. Maybe until we reach epoch 10 or 11. Please note that the loss function has now converged to a relatively acceptable value, and if we select the chart as XY plot, we notice a reasonable regression line. Here we show the velocity A and velocity B components. We also show these values as charts, which we can select here as velocity A and velocity B. That mostly covers this topic of stochastic gradient descent, or SGD algorithm. Feel free to play with this tool by using your data set, selecting various combinations of initial values, learning rates, batch sizes, momentum option, and observing the intermediate values and the important charts and plots, helping you understand the stochastic gradient descent better and faster.